Hello everyone, my name is Kazim and thank you for joining today's webinar. In today's webinar, we are going to discuss about AI-driven zero trust and autonomous security for the cloud era. During this session, we would request each every one of you to stay on mute. And if you may have any questions or concern, please feel free to drop them in the chat. After this session, I'll share the deck with you on your email address, and I would also have this session made available on YouTube. And I would address all your concerns right there for more visibility. Thank you. And without wasting much time, let me start sharing the deck and let's get deep dive into it. Thank you. So over the next 45 to 55 minutes, we'll explore something that's fundamentally changing how we approach security. We're not just talking about zero trust as a concept anymore. We are seeing AI transform it into something that can actually operate autonomously in real time across cloud environment. I've spent few years implementing this system and I want to share the same, both what works and what does not. So let me start with a story. Last year, we were consulting a mid-sized fintech company. They had invested heavily in firewall technologies, top of the line equipment actually, with a skilled team and the works. Then an engineer spun up a test database in AWS to experiment with a new feature, which he forgot about it. 3 months later, the database was compromised. The attackers was inside for 127 days before anyone could actually notice. The problem was not the firewall. The problem was the entire model of inside versus outside had become meaningless. Now, this company had 47 different cloud services, roughly, and a contractor accessing the system from 12 different countries. And the automated CI/CD pipeline deploying code every 20 minutes. The traditional parameter has dissolved. This isn't unique. Every organization we see this, they face this one. So the question isn't whether your parameter is porous, it's how quickly you can detect and respond when someone gets through. So zero trust sounds simple on paper, which means don't trust anyone or anything by default. But implementation is where things get complicated. I want you to imagine your typical employee's workday. Suppose an employee named Sarah logs in from home at 8 a.m. She accesses email, jumps on the Slack, opens the CRM, pulls up customer data, push code to GitHub, etc., etc. And that's quite a different system with different permission requirement. Now, in a traditional setup, when Sarah logs in at 8 a.m., she's trusted all day. But in zero trust, every single one of those action trigger verification. Is this really Sarah? Is this she using her normal device? Is she accessing from usual location? Does she normally access the admin panel at this point? Is the security posture compliant? So now multiply that by 500 employees, 50 application, or maybe some 200 API endpoints, thousands of automated processes. You can see why manual verification becomes impossible. This is where AI becomes not just useful but absolutely necessary. So here's where I'll be brutally honest. Zero trust without AI is trying to manually check every car at a border crossing during rush hour. Theoretically possible, but practically it's unusable. So I've worked with a couple of security team, a different healthcare provider, uh, roughly five highly skilled and analysts. The SIEM system generated about 3,000 alerts daily. After filtering false positive, they still had 200 to 300 events to investigate. Each investigation took 15 to 45 minutes. Now, you do the math, it's quite impossible. What made it worse was the real threats weren't the obvious one. An attacker who compromised an account would behave almost normally, just slightly off, maybe accessing files 15% more frequent than usual, or logging it at times that were within the person's normal range. But unusual for that day of the week. A human looking at logs would miss this. We needed a system that could learn what normal looked like for each user and flag deviation that were statistically significant but contextually suspicious. That's what AI brings to zero trust. The ability to establish baseline, detect anomalies, correlate across system, and make the access decision in real time. It is not replacing the human judgment, but handling the scale that makes zero trust practical. So this architecture diagram shows the heart of an AI-driven zero trust system. Let me walk through a real access request to show how this works in practice. Imagine Sarah from earlier trying to access the customer database at 2 p.m. on Tuesday. Here, here's what happens in the approximate 200 milliseconds before she gets access. First, the policy engine receives a request. It's not just checking does Sarah has have permission. It's asking should Sarah have access right now, given everything we know. The behavior analysis component has been watching Sarah for months. It knows she typically accesses this database between 9 a.m. and 5 p.m. on weekdays, usually from her office or home IP, and typically pulls 50 to 200 customer records per session. Now, the risk scoring module calculates real-time risk score. It sees location matches, fair, it's good. Device fingerprint matches, good. Time is normal, good. But wait, a VPN disconnected and reconnected 3 times in the last hour, slightly suspicious. And she just received an email with a suspicious attachment, which would, of course, increase some risk. The context aware component adds environmental factors. There's been a spike in credentials stuffing attacks against similar companies this week. Industry level threat elevated a little, and Sarah's team is working on a major project deadline, which explain the potentially unusual activity. All of this fits into the IAM system, which makes a decision, which grants access but requires step up authentication, maybe more like a push notification to a phone to confirm, reduces a session timeout from 8 hours to 30 minutes, and flag her activity for enhanced monitoring. Now, this entire process is autonomous, no human intervention, and it happens thousands of times per minute across the organization. Supervised learning. Now, let me get practical about the ML models because this is where theory meets reality. I've built and broken enough of this system to know what actually works. Now, the supervised learning is your workhorse for known threats. We train model on labeled data, millions of examples of malicious and benign activity. The model learns pattern. When you see the sequence of API calls followed by unusual data transfer volumes, that's probably exfiltration. These models are very accurate for threats we have seen before, but completely blind to novel attacks. Unsupervised learning is where things get interesting. This model don't need label data. They just learn what normal looks like for environment. I implement a system at SaaS company where we train isolated forest model on user behavior. The model learned that Bob from accounting always accessed the finance system between 8 to 10 a.m. He pulled reports and closed his session. When Bob's credentials were compromised, an attacker logged in at 3 a.m. and started accessing employee salary data, something Bob had never done. The model flagged it within 90 seconds. But here's the challenge. The unsupervised model generates a lot of false positive initially. In our first week, we had approximately 12% of false positive rate. People working on urgent projects, new employees, legitimate role changes, all trigger alerts. Now, this is where reinforcement learning saves you. We implemented a feedback loop where security analysts would mark alerts as true as false positive. The reinforcement learning model learned from this decision. Within 3 months, our false positive rate dropped from 12 to 3.8%. The model learned context. Late night deployments were DevOps during the last week of the month are normal. Random late night database access by HR, now that is suspicious. The key insight is that you need all three approaches working together: supervised for known threats, unsupervised for unknown threats, and reinforcement to continuously improve the system. Now, this code, represents the actual logic. Now, this is what we implemented in production system. Let us break down what's happening because the devil is in these details. First, notice we're not just checking credential. We're building a rich context object that includes user profile, device, fingerprints, location, resources, sensitivity, and temporal factors. This is critical. A login attempt is not just valid credential or invalid credential. It's a complex event that needs multi-dimensional analysis. The risk scoring uses three different models, and we weigh them differently. Before analysis get 40% weight because in practice it's been the most reliable indicator. If someone who normally works 9 to 5 suddenly logs in at 3 a.m., that matters. Anomaly detection gets 35%. It catches the weird stuff, but it's also noisy. Threat intelligence gets 25%, useful for known bad actors but limited to what we already know about. Now look at the decision logic. We don't just have allow or deny. We have graduated response. It's low risk. Full access with normal session length, that's medium risk. Access grant but with step up authentication and reduced session timeout, that's a high risk. Denied and we alert the security system. This graduated response is crucial for usability. Early implementation were too binary. User either got full access or were blocked entirely. This critical friction and workaround behavior, people would share credential or find backdoor system because the security was too restrictive. The adaptive control let us maintain security without destroying productivity. The explained decision method is also critical. When we deny access or require additional authentication, user and security team need to know why. Access deny is not enough. Access denied because unusual access pattern detected. Accessing sensitive resources, no recent MFA verification, help people understand and trust the system. One more thing about this code, see how the thresholds are parameterized. In production, this value get tuned continuously based on your organizational risk tolerance and the false positive rate you're seeing. Excuse me. There's no universal right threshold. A break might set it at zero point 0.5, a startup might set it at 0.8. It depends on your security posture and business need. Now this user behavior analytics is the foundation of AI-driven zero trust. Without accurate behavior baseline, your system is just sophisticated guesswork. And let me show you how we build this. Now we spent some time with this system for a tech company with approximate 800 employees. The first thing learned, every user is unique. Now Sarah's problem is completely different from Mike in sales or Dr. Johnson in research. A generic rules don't work. User shouldn't access the system after hours. Breakdown when you have global teams and on-call rotations. We start with the learning phase. For 30 to 60 days, the system just observes. It's building statistical model of normal behavior. For one of the users, Sarah, we discover she typically commits code between 9 a.m. and 6 p.m. on weekdays, with a spike right before sprint reviews. She accesses AWS console more frequently on Monday, well presumably reviewing weekend deployments. Now, her database queries follows a pattern. She runs them in the afternoon, rarely more than 50 at a time, and almost never on Fridays. But this pattern gets stored as a probability distribution, not rigid rules. We don't say Sarah works 9 to 5 only. We say there is a 95% probability she is working between 8 a.m. to 8 p.m. on weekdays, declining 20% on weekends. Now, this allows for natural variation while flagging through anomalies. The anomaly triggers at the bottom are critical. We categorize them by severity. If user suddenly tries to write to the customer database, something she or he has never done, now that's critical. Though they have the read access, since they have only the read access, so this suggests either credential compromise or privilege escalation attempt. Compare that to increased comment volume. Unusual worth noting, but could just mean she's working on a big feature. Here's some real example for a deployment. It detected that Mike, a sales engineer, logged into AWS console at 2 a.m. from an IP in Eastern Europe. Well, Mike has never accessed AWS before. His role did not require it. The system blocked access and alerted the security team within 30 seconds. Turned out his credential had been phished because we had solid baseline. We caught it before any damage occurred. The key to user behavior analytics success is continuous learning. People changes role, get new responsibilities, work on different projects. The baseline need to adapt. We update model weekly with a sliding window of the last 90 days. Now this keeps the current without over reacting to the short-term changes. This dashboard is what security teams live in. I'm showing you a text version, but in production, this is a full web interface with a real-time update, drill-down capabilities, and investigation tools. Let me walk you through a real incident which was caught with this dashboard. Look at the top entry. John Doe with a 0.89 risk score. Here's what happened. At around 2:23 p.m. on Tuesday, John's credentials were used to log into a document management system from somewhere in Europe. John is based in California. The system immediately calculated a risk score, high suspicion based on impossible travel. He logged in California 2 hours earlier, unrecognized device fingerprint and accessing a system he rarely used. But it did not stop there. Excuse me. Within 10 seconds, the attacker started downloading files, around 312 documents in rapid succession. Then our system model for John showed he typically downloaded 2 to 5 documents per session, maybe 20 on a busy day. The ML model detected this is a clear data exfiltration pattern. Now risk score jumped to 0.89. The system automatically blocked the session, revoked all John's active tokens, and sent alerts to a security team and John's phone. Total time from initial login to full lockdown, approximately 43 seconds. When John called 5 minutes later to report his laptop was stolen, we have already contained the breach. Now compare that to Maria, the yellow entry with 0.67 risk score. She accessed the admin panel at 9 p.m. on Saturday. Unusual, but she is an SRE on call this week. The system required step-up authentication. She will confirm via phone and limited her session to 30 minutes. Normal work or compromise? We don't know yet. So we take a balanced approach, along with enhanced monitoring. The anomaly type section at the bottom helps us spot trends. If we suddenly see a spike in the new device, location, or events, that might indicate a credential stuffing campaign. If privilege escalation attempts spike, we might have an insider thread or a compromised admin account. Now this dashboard also shows our false positive trend over time. When we first deployed, about 15% of high-risk alerts were false positive. Through continuous tuning and reinforcement learning, we have gotten down to under 4%. That's critical. If your system cries wolf of too often, people stop paying attention or find workarounds. This is one of the most important shifts in AI-driven zero trust. Authentication is not one-time gate at the beginning of your session; it's continuous throughout. But think about how authentication traditionally work. You log in at 9 a.m. with a username, password, and maybe MFA. Then you're trusted. And for the next 8 hours or until you log out. During that time, you can do anything your permission allows you. If your session gets hijacked at any point in the afternoon, let's say 2 p.m., the attacker has full access until 5 p.m. or until someone notices unusual activity. The continuous authentication changes this fundamentally. Every action you take gets evaluated. The system is constantly asking, should this user still have access given what we are seeing right now? Let me show you a real example from a healthcare organization where a doctor logs in at 8 a.m. A normal credential, normal device, and normal location. The risk score stays at 0.15, which is low risk. Now she accesses patient records throughout the morning. Each access is evaluated, but everything looks normal. Risk stays below 0.3. Now at 1 p.m., when the doctor tries to access the pharmacy system to check medication information. This is slightly unusual As the doctor is an oncologist, not a pharmacist, the risk score jumps to 0.52. Now, the system requires the doctor to re enter the PIN, which is a lightweight step up auth, and when he or she does, it continues working. Now, at 3 p.m., the doctor starts downloading patient record, not just viewing them, downloading as a PDF. The system sees 15 downloads in 10 minutes. Well, that's a normal pattern for a doctor for 1 or 2 downloads per day. Now, risk score hits 0.74. The system prompts for full MFA re-authentication. When the doctor completes it, and in the investigation, we found out that the doctor was preparing for a peer review presentation, which is quite a legitimate use. But if the credential had been compromised, we would have caught it within minutes instead of hours or days. The key factor that changed risk during a session are time lapse. When the longer session are more riskier. Sensitive action, behavior anomalies, and environmental changes. Now, this approach dramatically reduces the window of opportunity for attackers. Even if they compromise credential, they have to continuously behave like a legitimate user to avoid detection. And the more sensitive the action they try to take, the more likely they'll be caught. The challenge is balancing security with user experience. You can't ask for re-authentication every 5 minutes. People will revolt. Now, this AI helps here by only triggering re-auth when risk actually increases beyond acceptable threshold. Most users go through the entire workday without any additional prompt beyond the initial login. And now in this slide, just a minute, guys. I'm just scrolling over the document. Yeah. So now, with respect to adaptive MFA, now this is where AI-driven zero trust really shines in terms of user experience. Traditional MFA is blunt. Everyone gets the same treatment regardless of context. Now, adaptive MFA is more like a surgical. The level of authentication required matches the actual risk. Now, here's a story that illustrates why this matters. Working with a financial service company that had implemented this strict MFA across the board, every single login required password plus OTP from an authenticator app. Well, that sounds secure, right? The problem was that users were logging in 8 to 12 times per day. Different system, different application, session timeouts, etc. Now, each time, password that open up authenticator app, type in code, user experience was not so good then. Now, we saw people writing down passwords, sharing tokens, and even more concerning, they'll leave the session active indefinitely to avoid re-authentication. When we moved to adaptive MFA, the experience changed dramatically. Now, the user Sarah logs in from her home office at 8 a.m. Known device, expected location, normal times. The system requires just a password. Why? The risk is low. Everything about this login matches her established pattern. Now, but when Sarah tries to log in from a coffee shop Wi-Fi at 11 p.m., maybe on Saturday, now the system recognizes elevated risk, unknown network, unusual time, slightly unusual location. Now, this time it requires password plus notification to her registered mobile. Still not overly burdensome, but an additional verification that the person logging in actually has the physical device. Now imagine Sarah's credential get phished and someone in another country tries to log in. New device, impossible travel, completely different access pattern, risk score hits 0.92. The system blocks the attempt entirely and sends alerts. No amount of authentication factors will help. The context scream compromise. Now, the table showing risk factor is based on actual implementation data. Behavior pattern gets a high weight, around 25%, because in practice it's the strongest signal. A user behaving normally from a new device is less risky than someone behaving abnormally from a known device. The results speak for themselves. We reduce MFA prompt by 73% for legitimate user. Think about that. Instead of 12 MFA prompts per day, user now see 3 to 4. But we did not sacrifice any security. Detection rate for compromised credentials stays at 99.1%. We're catching the real threats while reducing the friction for normal operation. The user satisfaction improved by 68%. The support tickets and authentication issue dropped by 54%. People stopped complaining about security being in the way and start seeing as an intelligent protection that understood their context. The key insight in this, security and usability aren't opposite. With AI, you can have both. The system adapts to the actual risks, which means high security when you need it and low friction when you don't. Now, the network segmentation is another area where AI transforms zero trust from theoretical to practical. Now, traditional segmentation is like building walls between departments. AI driven micro segmentation is like having an intelligent security guard at every doorway who knows exactly who should be talking to whom. Let me explain the problem first. In traditional network, once you're inside, you can often reach many systems. If an attacker compromises on web server, they can potentially pivot to other servers, databases, and internal system. This lateral movement is how small breaches become massive data thefts. Well, we work on a breach investigation where attackers got in through a vulnerable WordPress plugin in a marketing website. The server was on the internal network. From there, they discovered and compromised the email server, then pivoted to file server, eventually reaching the databases containing customer payment information. The initial compromise took them 10 minutes. The later movement took 3 months because no one noticed. By the time we discovered, they had access to nearly everything. The micro segmentation prevents this by implementing it manually. It's nightmarish. You need to map every legitimate communication flow in your infrastructure. For a company with approximately 200 applications and services, that tens of thousands of rules to define and maintain. When someone deploys a new service or changes an application, those rules need updating. Most org give up because it's too complex. Now look at the Python code example. The AI built this behavioral models for every service. I know that the database should accept connection from the API gateway and admin console, but never directly from the web app or user devices. If suddenly the web app starts making the direct database connection, something it's never done, that's a huge red flag. Probably an SQL injection or a compromised application server. Now, in one deployment, we had a compromised API server that started scanning the internal network looking for other systems to attack. The AI detected this immediately. The API server had never initiated connection to those internal APIs before. We isolated it within 12 minutes. Compare that to the industry average of 2 or 4 days to detect and contain a breach. Now, the automatic policy generation is also huge for operational efficiency. Instead of spending months mapping and configuring segmentation rule, the AI does it in a week and with minimum human intervention. Now, this is zero trust at the network level. Every connection is evaluated based on identity, context, and learned behavioral patterns. Not just are you on the internal network, but you should specifically be talking to this specific service right now. Threat intelligence integration is what makes you AI driven zero trust system aware of the broader threat landscape. Your internal models are great at detecting anomalies with your environment, but they don't know what external threats until those threats hits you. Threat intelligence changes that. Here's a scenario that happened to a company. On a Tuesday morning, they got a notification through threat intelligence feed that a major breach had occurred at a competitor in the same industry. The attacker had stolen 150,000 user credentials and were actively attempting to use them across other healthcare companies. Now, the AI system immediately adjusted its risk model. It increased scrutiny on password age if someone was using an old password that hadn't been changed recently. They was now riskier. It enhanced monitoring for email domains and a pattern similar to the breached company. It lowered threshold for rate limiting to catch credential stuffing attempts were more aggressively. Now, within 25 minutes, we started seeing logging attempts with credential from the breach. The AI correlated the leaked password hashes with incoming logging attempts. When someone tried to log in as a John using a password from the leaked database, the system recognized it instantly. The login was blocked before John even knew his credential had been compromised. But the system did not stop there. The system proactively scanned our user database to find anyone else using similar password or pattern. We found roughly 47 users potentially at risk and forced password reset for all of them. We also scanned historical logs to see if any of this compromised credential had been used successfully in the past. Now, fortunately, we caught it before any successful breaches. This is the power of combining internal AI model with the external threat intelligence. The internal models detect anomalies and behavior changes. The external intelligence provides context about current threats, attack, campaign, and compromised credential. Together, they create a security system that's aware of both your environmental and the broader threat landscape. Well, let's walk through another example. When the Log4j vulnerability was announced back in December 2021, organization had hours to spend before Mars exploitation began. Our threat intelligence feed picked up the CVE within 10 minutes. The AI system immediately scanned our environment for application using Log4j, increased monitoring on the system for exploiting attempts, and it applied temporarily compensating control, where like more blocking specific payloads at the network level, and prioritize patching for high risk system, enhance login for forensic analysis if we have already been compromised. Now, by the time the first exploitation attempt hit our system, 4 hours later, we were already protected. The vulnerable system were patched or isolated, and the AI was watching for a specific attack signature. The key here is automation. Threat intelligence is only useful if you can act on it quickly. Getting an alert about a credential breach is nice, but if it takes you 3 to 4 days to respond, the damage is already done by it. AI enables real time correlation and automated response at a human's speed that humans can't match. Now, let me be honest about something that doesn't get discussed enough in security conferences. AI driven security system generates a lot of false positive initially. If someone tells you their system is 99% accurate from the day one, then they have not tuned it so conservatively that it's missing real threats. Look at those initial deployment stats. In the first 30 days, we generated 2,847 alerts. Only 43 were actual security issues. That's a 98.5% false positive. We blocked 847 legitimate users. The security team spent around 1680 hours investigating false alarm. Now, obviously, people were furious. We got emails from executives saying the AI is worse and than having nothing. And they went completely wrong. A security system that blocks legitimate work is a broken security system. But here's the thing, that's expected in the learning phase. The AI does not magically understand your organization on day one. It needs time to learn and it needs human feedback to improve. The key is the feedback loop. Every time an analyst investigates an alert, they mark it as a true positive or false positive and explains why. Now, this is a false positive because a user just changed the role and this access is now part of their job. This is a false positive because we always see increased database activity at the month end for financial reports. Now, the system learns from this feedback. Now, look at the code. We're not just collecting feedback, we're analyzing it excuse me, to find patterns. If we see that 50 false positive are all related to role change, then that tells the model it's too sensitive to role change. We adjust it. Now, after 6 months of manual tuning, we got alerts down from 2,847, which was earlier, to 892. Well, quite better, but still 95.7% false positive. Now, the breakthrough came when we implemented reinforcement learning with a proper feedback mechanism. The reinforcement learning model, in which the model learns which types of alerts are most likely to false positive and adjusts its scoring accordingly. It learned that when 50 plus users simultaneously show the same anomalous behavior, it's probably a new business process or a tool, not 50 simultaneous compromise. It learned that after hours access during the last week of the quarter, it's normal for the finance team. It learned the new employee needs a different baseline period before anomalies are meaningful. Now, after 12 months, we got it down to 287 alerts with 14.3% true positive rate. Well, that still we cannot call it as a perfect, but we are still generating false positive, but it's manageable. The security team now can actually investigate 287 alerts per month, and we are catching the real threats. The table at the bottom shows the most common false positive causes we encounter and how we solve them. Role changes were huge. People get promoted, change team, takes on new responsibility. If a system does not know about HR changes, it'll flag all of the suspicions. We integrated with the HR system to the AI So the AI system knows when someone's role change and give them a grace period to establish new pattern. Now the honest truth is that the false positive reduction is an ongoing process. You never get to zero, but with proper feedback loop, reinforcement learning and continuous tuning, you can get to the level where the system is actually helpful rather than just generating noise. And here's the important part, even with false positive, we are still catching threads that would have been missed entirely without the AI. Those 41 true positive included compromised credential, insider threats, and attempted data exfiltration. Without the AI system, most of those would have gone undetected until it was too late. Now, this is the uncomfortable conversation that needs to happen when implementing AI driven zero trust. You're monitoring everything users do. That raises serious privacy and ethical questions that you cannot ignore. Now, I've been in meeting where executives get excited about the security benefit, and then someone from legal or HR asks, wait, are you tracking every single thing our employees do? Every file they access, every system they log into, everywhere they go? That sounds like a surveillance. And why? And they're not wrong. It's, I guess, surveillance in a sense. The difference is intent and scope. We're not monitoring what users are doing. We're monitoring metadata when, where, and how much. They don't read the emails or capture the screenshot. We track that they logged in at certain time from a certain location and downloaded, let's say 500 customer record, which is anomalous. But intent does not eliminate legal obligation. So look at what we collect: authentication attempt, access pattern, data movement, location data, behavioral patterns. Under GDPR, that's personal data, and under CCPA, it's a covert. Under various employment laws, it may require notification as a consent. The compliance framework I'm showing here is what we have implemented across multiple org. The key principle, data minimization. We collect what necessary for security and not everything we technically could. Time limited storage. We don't keep detailed logs forever. Real time analysis happens on a live stream. Access control. The security team sees anomalized data. User IDs are hashed. They see user XYZ access database at unusual time, not John Smith access database. Now, only during active security investigation with proper approval do we anonymize to identify the specified user environment. Now, for GDP, we caught a real insider threat, excuse me. But imagine if we have mishandled the data, if we have shared it with their current manager before the investigation was complete, if we have used it for performance management rather than security, the privacy violation would have been severe and we have been exposed the company to significant legal liability. Now, for GDPR compliances, we conducted data protection impact assessment before deployment. Now, moving to the next slide. Now, there is another implementation story which I want to share. Not the sanitized marketing version, but what actually happened with all the messiness and the challenges. There was a healthcare SaaS company about roughly 1,200 employees handling sensitive patient data. They've had a rough year security wise. Three major incidents, including a credential compromise that went undetected for 47 days. They were bleeding money on incident response and facing serious compliance pressure from customer and regulators. When we started planning, the immediate reaction from the board was, how fast can we deploy this? They wanted it roll out company wide in 30 days. I had to have difficult conversation. That's not how this works. You can't go from zero to AI driven zero trust in a month. The ML model needs time to learn your environment. User need time to adapt. The security team needs training. Now we planned a 6-month implementation with another 6 months for optimization. The board was not thrilled, but they agreed after I showed them what happens when you rush security project. System that generates so many false positives they become useless. In the first 2 months we were planning, we accessed the current state, which was a mess, honestly. A VPN based access with no real visibility when someone was inside. Manual access reviews that were 3 months behind. No integration between security tools. Now, in the third and fourth month, with a pilot with 50 users, with IT and security, this was intentional. because we want to start, or it has to be started, with a technical team who understand what we are doing and can provide sophisticated feedback. Good thing we did, because we discovered our initial threshold were way too aggressive. We were blocking legitimate admin activities and generating 40 plus false positive alerts per day. The ML model hasn't learned that, but normal admin behavior look like, because admin behavior is inherently more variable than regular user. We spent those months tuning and learning. We documented every false positive, adjusted threshold, improved our integration with the ticketing system so the AI could actually understand plant maintenance window and refine our incident response playbook. Then, in the fifth and sixth month, with the rollout phase, we learned from other failed security projects that you can't just flip a switch organizational wide. We roll out in waves. Technical team first, of course, then business operation, then contractors and partners. Sorry. Now each wave took 2 weeks, or with a week in between for adjustment. The rollout was not smooth. During the wave two, we had an incident with 30 people from the finance team got blocked for a day, well, for a quarter of the last quarter, because they were working late, accessing system beyond the normally work hours. The AI saw 30 anomalies and they got aggressive because of the block and the last month activity which was pending for them. Now look at the result though at the table. After 12 months, we reduced security incident by 87%. But more importantly, look at the detection time from 47 days to 8 minutes. That's a real game changer. We're catching things in real time instead of discovering breaches months after they happened. The three specific incidents at the bottom are real. The contractor credential compromise happened in month 8. Someone fetched a contractor, got the credential, and tried to log in from a botnet IP. The system detected it in 45 seconds. Because it was an impossible traveler, the contractor logged in from Seattle, but now they see the login from from Romania, which is unknown device, unknown usual access pattern, and it got blocked immediately. Now, the insider threat case was even more interesting. An employee in customer success had been downloading patient records for a week before giving their resignation notice. Now, our system detected that their downloaded volume had increased 400%, that they were accessing records outside the normal patient portfolio. We caught that mid-download, terminated the session, and alerted the HR, and it turns out that the employee was going to join a competitor and trying to take patient data with them before leaving. But the lesson learned section is what I wish someone had told us before we started. User communication was our biggest early failure. We thought we have communicated enough. We sent emails, had town halls, updated documentation, but that wasn't enough. Users were confused and frustrated when they got additional MFA prompt or access denial, which we had to do on a second wave of education with specific example of why the system was doing what it was doing. Now, the seasonal pattern issue was something we should have anticipated, but did, but we did not, because retail clients had very different behavior during holiday shopping season. Healthcare clients had different pattern during flu season, and tax and accounting clients were crazy in March and April. Now, our initial ML model did not account for this clinical pattern. We had to implement time series analysis with seasonal decomposition. But despite all the changes, it worked. The security team went from drowning in alerts to actually being able to focus on real threats. But the key success factor from the cross-functional team, security could not do this alone. We needed IT for integration, legal for compliance, and HR for role data, and privacy for GDPR and CCPA compliance, and executive sponsorship for resource and organization buy-in. Any AI driven zero trust implementation that just a security project will fail. It has to be rather an organization transformation. Now let's get into the technical details of actually building the system. This is the ML pipeline architecture we use in production, and I'm going to walk you through each layer because the devil is inside this implementation detail. The data ingestion layer is where everything starts. You need to collect event from everywhere. Your cloud provider, your SSR system, endpoint security, network flow data, application log, etc. etc. Now, in our implementation, we are ingesting about 50,000 events per second at peak. That's roughly 4 billion events per day. Now we use Apache Kafka for stream processing because we need real-time analysis. Traditional batch processing does not work for zero trust. You can't wait until tomorrow to detect that someone credential were compromised today. And then Kafka lets you process events as they happen with a sub-second latency. But the feature engineering layer is where most of the magic happens. And it is also where most implementation fail. Raw log data is not useful for ML model. A user logs in at a 223 from some IP does not mean much by itself. You need to transform that into meaningful features. Look at the Python code for the engine. We extract temporal features. It is during business hours. It's a weekend. We extract behavior features. How often has this user logged in from this location? How many different locations do they typically use? We calculate location entropy. User have always logged in from the same place, or how have low entropy. User who travel frequently have high entropy. Now the velocity feature critical for catching compromised credential. If someone logged in from California 2 hours ago and now they are logging in from Romania, now that's physically impossible. We calculate the distance and time between logins to detect impossible travel. The peer group feature helps reduce false positive. Now, if everyone in the DevOps team is logging at 2 a.m. for a deployment, that's normal for that group. If someone from HR logs in at 2 a.m., that's unusual. The rolling window feature look at recent activity. How many login in the last 24 hours? Any fail attempts in the last term? This catches pattern that wouldn't be obvious looking at individual events in isolation. Now, all of this feature get calculated in real time and stored in a feature store. We use Redis for low latency access, but when an access request comes in, we need to make decision in under 100 milliseconds. We can't afford to recalculate everything from the scratch. Now, each model gives us a score, and we combine them with weighted login. In practice, we weigh the anomaly detector highest 60%, and it catches the normal attacks. We haven't seen that before. That clarifies get 40% weight for catching a known pattern. The interference need to be fast. We have the SL of 100 millisecond for risk scoring. That means optimized model, efficient feature retrieval, and sometimes model quantization to reduce computational overhead without sacrificing too much accuracy. Now the model versioning is critical. Sometimes a new model performs worse than the old one. Maybe better on an average, but worse for a specific use case. That's important to your org. You need to be able to roll back quickly. Now, one thing I want to emphasize about the feature engineering code, notice how much domain knowledge goes into it. The feature we extract aren't just statistical transformation of the data. They encode security expertise, impossible travel, peer group comparison, sensitive escalation, velocity checks, etc. You can't just throw raw data at a neural network and expect good results. You need security experts and data scientists working together to design features that capture what actually matters for security. Now, performance and scale are where many AI security projects fail. You can have the most accurate ML models in the world, but if it takes 5 seconds to make an access decision, user will revolt and find workarounds. Well, let's walk through a performance number. We have a SLA of 100 milliseconds for risk scoring. That's from when a user clicks login to when we have evaluated their risk and made a decision. Now, our average is 47 milliseconds, and even at the 99 percentile, we are at 89 milliseconds. We're meeting our SLA, but it took a lot of optimization to get there. When we first deployed, our risk scoring was taking 800 to 1200 milliseconds, which is completely unacceptable. Now, the user noticed the delay, and we got complaints. We had to optimize aggressively. The biggest win came from feature caching. Calculating a user 90-day behavior baseline is expensive. It requires requires querying milliseconds of historical events, calculating statistic, building probability distribution. Now that was taking 40 milliseconds per evaluation. But here's the thing: a user baseline does not change that much minute to minute. We implement a 5-minute TTL cache. Now we calculate it once and reuse it for 5 minutes. Now The caching high rate is 85%, and cache hookup take 3 milliseconds instead of 40 milliseconds. The model quantization was another big win. Our random forest model we're using 32-bit floating point numbers. We quantize them to 8-bit integers. The model size dropped from 450 MB to 1100 MB, important for memory efficiency when serving many concurrent requests. Now, inference time dropped from 35 milliseconds to 18 milliseconds. The accuracy loss was only 0.3%, which is totally accepted for the performance gain. Now, we also had to get smart about what we need, real time evaluation, and what can be batched. Authentication decision need to be real time. User are waiting, but historical analysis, compliance report, and trend analysis can be batched and processed overnight. Now, this reduce our real time processing load by about 40%. Now, look at the capacity planning session. This is crucial for budgeting and scaling. We started with 1200 users generating 500,000 access requests per day. As we scale 500 users, that grows to 2.1 million requests per day. That's a 4.2x increase. But infra does not scale linearly. We need to account for redundancy, peak loads, growth, headroom. Now, the cost is important to communicate to leadership. Going from 1200 to 5,000 user increase the infrastructure cost from roughly 12,000 to 38,000. That sounds expensive until you compare it to a cost of a single breach, typically 125,000 to some millions, maybe five, depending on the severity. The model accuracy drift is subtle but important over time as user behavior changes, as new applications are added, as the threat landscape evolves. Model accuracy can degrade. We track accuracy on a held out validation, which is set every day. If it drops more than 5%, we trigger an alert and accelerate the retraining schedule. And one last thing about the scale, we tested our system at 10x expected load. Load testing in security system is tricky because you need realistic data, not just synthetic load. We replayed historical events at 10x speed and verified the system still perform within the SLA. Now this gives us confidence that we had a headroom for growth and could handle traffic spike during incident. That brings to the end of the session, and I appreciate each one of you taking time. Thank you so much for your attendance. Mike, I would be sharing this deck to you guys personally, as I have your email on the form which you guys filled in, and I would also share the link when I host this on the YouTube. And you can feel free to connect me on LinkedIn, and there's a quick link to my GitHub uh, account. There are a couple of there are few actual projects which I was working on, and feel free to comment on those too. Thank you again.